Okay, let's talk about the fundamental counting principle. So, the fundamental counting principle says when there are m ways to do one thing and n ways to do another, there are m times n ways to do both. So, we're going to use the fundamental counting principle to determine how many ways there are to choose from multiple options. So, for example, one, it says Rhiannon here has two pencils. One has glitter and one has stripes. She has three eraser tops, blue, pink, and purple. How many different combinations of pencil and eraser does she have to choose from? So you can do this one of two ways, but they basically all end up being the same thing. So you can map it out, right? If she has two pencils and one is glitter and one is stripes, with each of those pencils, she could use one of three eraser tops, blue, pink, or purple. Right, so you can use a green or a glitter pencil with blue, pink, or purple erasers, or she can use a striped pencil with blue, pink, or purple erasers. So how many different combinations of pencil and eraser does she have to choose from? Well, there's six, right? Three from the glitter pencil and three from the striped pencil. But there's an easier way to do this. You can just multiply the options you have. We have two pencils times three eraser options equals 6. And that is how many different combinations she can make of pencils and erasers. So you can always map out the different choices, different options, which can be logically an easy way to do that. But you can also just multiply the number of ways to do each thing together. For example, B says Robert has black or brown socks. So two sock options. Three pairs of pants, jeans, khakis, and shorts. Three pants options. And three shirts, red, blue, and black. Three shirt options. How many different outfits can he make? 2 times 3 is 6, times 3 is 18 outfits. 18 technically different outfits. Whether you have black or brown socks on might not even be noticed, but it is technically a different outfit. Okay, a new ice cream shop is keeping it simple. They offer 3 flavors, chocolate, vanilla, or strawberry. For toppings, they have peanuts, sprinkles, caramel, or fudge. And finally, they serve their ice cream in bowls, cones, or waffle cones. How many combinations of ice cream can a customer order? Assume one flavor, one topping, and one container. So this last part is very helpful because, when you go to an ice cream shop, you can get one, two, three, however many scoops you want. But we're going to assume one flavor, one topping, one container. So they have 3 flavors times 4 topping options times bowls, cones, waffle cones, 3 container options. 3 times 4 is 12, times 3 is 36 different combinations of ice cream. Now, sometimes you have to slightly adjust your process here depending on a couple of things. So there's 2 types of events that can happen, independent and dependent events. For independent events, the outcome of one event does not affect the outcome of another. For example, if I'm flipping a coin and rolling a die, whether I get heads or tails on the coin doesn't affect the number I get on the die. I have 2 choices for the coin, 6 choices for the die. That's never going to change. For dependent events, the outcome of one event does affect the outcome of another. For example, choosing names out of a hat. Once I choose the first name, it's no longer an option. So I have fewer options for my second draw, and so on for my third. So we'll do a similar process here, but we have to state whether the events are independent or dependent, and that might change our multiplying process. So the first example says Seth has to take 5 classes next semester. He can choose from chemistry, math, biology, English, art, or science. So that's 1, 2, 3, 4, 5, 6 class choices. For this example, we'll assume that all these classes are equally necessary and important. He can choose whichever ones he wants. If each class is offered every period, how many schedules can his counselor make? So we have to think through this. We have 6 class options. So he has to take 5 classes. 1, 2, 3, 4, 5. Now, first he has 6 choices. So he can take any one of 6 classes. But once he chooses one, he can't take that class again. I can't take 5 sections of chemistry 1. So then we have 5 choices left. And then we have 4 choices left. And then 3, and then 2. So I have to do 6 times 5 times 4 times 3 times 2. 6 times 5 is 30, times 4 is 120, times 3 is 360, times 2 is 720 possible schedules, assuming there's no other constraints on it for this schedule. So these are dependent events, because the choices I have each time I choose a class gets smaller. The outcome of the first event, choosing a class, does affect the outcomes of the others. Namaya bought a new 4-digit lock for her bike. How many different combinations are possible? So we have a 4-digit lock. And the digits 0 through 9 mean there are 10 options for each digit. Now these are independent events because I could have a 4-digit code that's all the same number. So I have 10 options for each digit on the lock. So choosing a 1 for the first digit doesn't mean I can't choose a 1 for the next one. So it doesn't affect each number going down. So I have 10,000 different combinations of this lock, and these are independent events. Okay, so that's the difference there. If you have an independent event versus a dependent event, the outcome of the independent events don't affect each other, but with the dependent events, they do. And so that will just depend on the problem you have or the situation you're working with. In both cases, you find the total number of possibilities by multiplying the individual possibilities together. So, but with dependent events, each one will affect the number you have for the next one.